Good morning, students. Myself, Vijay Shankar from UC Department, Chipro Engineering College. Today, we are going to discuss the continuation of sampling theorem. In the last class, we derived the expression of the Fourier transformation of the x delta of t. That is nothing but x delta of f is equal to fs into the sum of n is equal to minus infinite to infinite x of f minus n into fs. Okay. So this is the equation we derived in the last class by taking off the time domain function. X delta of t is equal to sum of n is equal to minus infinite to infinite delta of t minus n into ts x of n into ts. The time domain function convert into the frequency domain function by using the trigonometric Fourier series. X delta of f is equal to f into the sum of n is equal to minus infinite to infinite x of f minus n into fs. Okay, here fs x of f is a Fourier transform of the original signal x of t. This equation shows that the process of uniformly sampling a continuous time signal results in a periodic spectrum with a period equal to the simple rate fs. It's a periodic function. Periodically, it is repeated with a time period of ts or the simple rate of fs. We know that ts is a sampling period. 1 by fs is in the terms of the frequency. Okay. Here the x of f is a Fourier transform of the original signal x of t. This equation shows the process of uniformly sampling a continuous time signal results in a periodic spectrum with a period equal to the simply the rate fs. That is the equation, the Fourier transformation of a signal x of t results in x of f minus n into fs. In the function C here, the x of f minus n into fs. It depends upon the n value, where n is equal to 0, n is equal to 1, and n is equal to 3, and so on. Positive values, x of f minus n into fs is equal to x of f ohm. At f is equal to 0, not the f is equal to 0, and plus or minus fs, and plus or minus 2fs, and plus or minus 3fs. So when I am taking the when n is equal to 0, it becomes of x of minus n into fs. When n is equal to 0, the value becomes x of f ohm. Okay. When n is equal to 1, the function x of f minus fs. So when n is equal to 0, the spectrum look like with the band limited signal of fm, that is nothing but a minus fm, 0 and fm. Now when n is equal to 1, the x of f signal is shifted with the left side with the samples of fs. Means whatever the 0 here, now the spectrum is when n is equal to 0. And the spectrum when n is equal to 1, the 0 value is shifted to the fs value. This is a fs. Now the same fs is 0. 0 is shifted fs, and here also the fm, and here the minus fm is minus fm. So fs plus fm becomes fs minus fm. Got it, my friends? So the total spectrum is shifted towards the right side with the samples of fs. 0 is changes to the fs here, and fm means 0 is increases fs, fm is also increases the fs, and the minus fm is fs minus fm. Suppose if I am taking the left hand side as a periodic signal, when n is equal to -1. When n is equal to -1 means when n is equal to -1, what is the function we have? The x of f plus fs. Plus means advanced function. Means the total spectrum what we taken from -fm to the fm is shifted towards left hand side. The 0 now it becomes of -fs, because the value of n is equal to -1, minus of minus. Now this function is -fs plus fm, and the term is -fs minus fm. Like this, we will get the spectrum whenever if you can take as x of f minus n into fs is equal to x of f, at f is equal to 0, plus or minus fs, plus or minus 2, and plus or minus 3. This is for plus fs, and this one is a minus fs. You can take the next spectrum when n is equal to -1, -2 here, it becomes of -2fs. And similarly, in the right hand side, we can take the spectrum either +2fs. So periodically it is repeated, the right side or the left side is shifted towards. We're considering when n is equal to 0, n is equal to 1, n is equal to -1, and so on. Thus the same spectrum x of f appears, listen carefully my dear students, thus the same spectrum x of f, whatever I assume here, this is x of f. And this one is x of f minus fs. And this is a spectrum of x of f plus fs. And this one is x of f plus 2fs. The totally you can combining the sum of n is equal to -infinite to infinite x of f minus n into fs. Okay, thus the same spectrum x of f appears at f is equal to 0, f is equal to plus or minus fs, f is equal to plus or minus 2fs, etc. This means that a periodic spectrum with a period equal to the fs is generated in the frequency domain. So periodic spectrum with a period equal to fs is generated in frequency domain because of sampling x of t in the time domain. Sampling x of t in the time domain. Otherwise, if x of t would not have been sampled, then there would be only one spectrum x of f around the f is equal to 0. If it is not sampled, what is the original signal? Having only the one signal is there, that is from -fm to 0 to the fmo. The x of f only we have the x of f. If it is a sample, there is a spectrum we'll get when n is equal to 1 and n is equal to -1, and n is equal to 2, n is equal to -2, so on. Understood, my dear students? So very carefully you can understand. Listen carefully, my dear students. It is very, very difficult and very easy also. Then, so the equation 514, previous equation here, 514, the x delta of f is equal to fs into the total sum of n is equal to -infinite to infinite x of f minus n into fs can be written as x delta of f is equal to, after expanding the function, fs x of f when n is equal to 0 here, this is the equation when n is equal to 0. And this one is when n is equal to plus or minus 1. And this one is for n is equal to plus or minus 2, and so on. This equation, this expansion shows that every term in the sum is the same spectrum at multiple sampling of the frequency fs. And this equation, so what is the equation here we have? The x delta of f is equal to fs into sum of n is equal to minus infinite to infinite, x of f minus fs, n into fs, sorry, n into fs minus. Now I'm expanding this function as when n is equal to 0, you can substitute n is equal to 0, fs into x of f only. When n is equal to 0, that becomes total function is a 0, x of f plus, and sum of n is equal to, it is a minus infinite to infinite. Again, if I'm taking minus infinite to infinite and not equal to 0. I already taken the when n is equal to 0 this one. When n is equal to 0, this function will get. So fs into x of f minus n into fs. Okay. So the remaining functions, when n is equal to minus 1 plus 1, minus 2 plus 2, minus 3 plus 3, and so on. But n is equal to 0, already we take fs into x of f. So x delta of f is equal to fs into x of f plus sum of n is equal to minus infinite to infinite, fs into x of f minus n into fs when n not equal to 0. In this equation, the first term represents the spectrum that would have been obtained without sampling. The first term is the fs into x of f. The first term represents the spectrum that would have been obtained without sampling, and the rest of terms under summation represents the spectrum repeating at multiple frequencies of a sampling frequency fs, repeating frequencies with the period of fs. By the definition of the Fourier transformation, we know the Fourier transformation of the continuous time signal is the Fourier transformation of x of t is integral minus infinite to infinite x of t power minus j omega angular frequency. Now it is a 2 pi f into t dt. And the Fourier transformation of the delta function, delta of t, x delta of t, the sum of n is equal to minus infinite to infinite, x of n into ts e power minus j 2 pi of f into n into ts. Okay. The above equation gives a Fourier transformation of the discrete time signal, hence it is called discrete Fourier transformation. In the above equation, t is replaced by n into ts because it is sampled towards the right side and the left side. Okay. Let us consider the signal x of t strictly band limited with no frequency. Let us consider the signal x of t is strictly band limited with no frequency components higher than the omega hertz. Strictly band limited. The sampling theorem statement is saying that a signal which is band limited to FM hertz, a signal which is band limited to FM hertz is completely recovered by its samples at a rate of fs is greater than or equal to f. So first of all, if I am taking that, let us consider the signal x of t is strictly band limited with no frequency components, higher than the omega hertz. There is no any signal higher than omega, nothing but it is a FM. Which is a signal which is band limited to FM hertz, either from minus omega to the plus omega or minus FM to the FM. That is, the Fourier transformation of x of m of x of t has property that the magnitude of x of f is equal to 0 for f is greater than or equal to omega. Totally the 0 value matters. There is no any component or the no frequency components higher than the omega hertz. Totally it is a 0. Means the x of f is equal to 0 when the frequency, let us take it is a w, or if it is in terms of minus fm to the fm, means the value is a frequency in the hertz. So greater than or equal to the omega. But it matters. The spectrum of such a signal is shown in the figure 5.1.2a. In the next page, you'll get the shape of the spectrum is just arbitrary and it taken because it is convenient for explanation. Let the sampling frequency be exactly equal to the twice of the maximum frequency. The first case, if I am taking the which is fully recovered or completely recovered by the sampling frequency is FM is greater than Fs is greater than or equal to 2FM. Okay. First of all, the signal, the x of f is equal to 0 for f is greater than or equal to omega, means is a original signal. There is no any frequency component higher than the omega hertz. Now, let us sampling frequency be exactly equal to the twice of the maximum frequency. See, the Fs is greater than or equal to 2FM. One case is Fs is greater than the 2FM. Another case is Fs is less than, not the less than, equal to 2FM. The two cases are greater than or equal to this. In this, the first case, the frequency be the exactly equal to the twice of the maximum frequency in the x of t. So Fs is equal to 2 omega, the 2FM. Got it, my students? So here the omega is the maximum frequency. FM is nothing but the maximum frequency. Okay. So this is a diagram. There is no any frequency component greater than the omega in the spectrum of a band limited signal x of spectrum of band limited. A signal which is band limited to FM hertz is completely recovered by its samples at a rate of Fs is greater than or equal to FM. The equation shows that the x of f will be reproduced when f is equal to 0, f is equal to plus or minus Fs, f is equal to plus or minus 2Fs and so on. The first case, if I am taking the Fs is equal to 2 omega, nothing but Fs is equal to 2FM or omega is equal to 2FM or the maximum frequency. Omega is nothing but the maximum frequency. The Fs is equal to 2FM means we can write as Fs minus FM is equal to EFM. Whatever here saying that Fs is minus omega is equal to omega. Okay, when you can take this in the right hand side, Fs is equal to 2FM. Fs minus FM. Okay, so how we'll get this spectrum of the sampled version of x of t? Let us assume Fs is equal to 2FM. Okay, omega is equal to, remember that here it is omega they are representing. I am explaining with the FM. So omega is equal to FM. Keep in mind the omega is equal to FM. Got it, madam? Means the minus omega is a minus FM, plus omega is a plus FM. This is for x of f when n is equal to 0. When n is equal to 0. Whatever the signal here, the minus omega to the omega is the same. How we get it is a repeated signal in the next one. So let us assume EFM is equal to or EFS is equal to, not EFM is equal to, EFS is equal to 10 kilohertz. 10 kilohertz. Listen carefully, my students. I am assuming the 10 kilohertz. Means Fs is equal to 2 into FM. FM is the 5 ohm. Okay. What is the FM? Now Fs is equal to, I am assuming 10 kilohertz. Means 2 into 5. 5 kilohertz. That is equal to 10 kilohertz is the FM. Fs sampling frequency. Okay, my dear students. My means what is the FM here? FM is equal to 5 kilohertz. That is FM is equal to 5 kilohertz in the right hand side. And in the left hand side is a minus 5 kilohertz. Okay. Now, in the equation, we are showing that when f is equal to 0, and the second case, f is equal to plus or minus fs. So x of f minus n into fs equation. Okay, my dear students. When n is equal to 1, what is the function now? It is representing as x of f minus fs. Minus fs. When n is equal to 0, when n is equal to 0, the value equation is a x of f1. So this is the equation when n is equal to 0. Now I am taking when n is equal to 1. When n is equal to 1, this is same x of f is shifted with the samples of fs. It's towards the right side. Towards the right side. What is the fs now? It is shifted with the 10 samples here. That value is omega is a 5 kilohertz, and this is a minus 5 kilohertz. What is the fs here? I'm assuming the 10 kilohertz. Let us take this fs is a 10. Means totally this 0 point is shifted to the 10. So what is the point of the next point of this value? What is the point here? 10 plus the omega. The fs is 10 plus, what is it? 10 is the fs frequency plus 5 omega. Here the omega is there. What is the omega is 5. Or omega is something but fm. 10 plus 5, it is a 15 point, this one. And this value is a 5 1. Okay. 5, 10 and the 15 means in between the difference is a omega is a 5 and omega is also the 5. Total is 2 omega. Okay. The total spectrum, it is a omega and omega, that is a 2 omega. Here also see 0 to 5, the 5 is difference. Minus 5 to the 0, it is also the 5 difference. Totally the 10. Okay. Here also the totally the 10. Omega is equal 5 into 5. 2 into that is a fs is a 10. And similarly, you can shift this at 2 fs means fs is a 10. What is a 2 fs is a 20. 20 and 15, there is a difference is a 5 here. 20 and 2 difference is a 5 means the value is a 25. So here fs plus omega and 2fs, the value is 2fs plus 5, nothing but fm. Okay. Fs is a 10, 10 into 2 is a 20, 20 plus fm is a 5, 25. In the left hand side also, when n is equal to minus 1, when n is equal to minus 1, what is the equation? We get x of f plus fs. Got it, my students? Plus fs means shifted towards the advanced function. Plus means the advanced signal. Shifted towards the right side. Okay, minus fs. Minus fs means what is the fs is a 10 kilohertz, minus fs is a minus 10. Minus 10. What is the value here? Minus 10 plus means these are minus fs plus fm. Okay. And this function is also minus fs, not the fs, fs minus fm. What is the fs here? 10. 10 minus fm is a 5 is a 5. So fs plus fs and fs minus fm. Okay. And here the fs minus fs plus fm and minus fs minus fm. Minus fs is a minus 10. Minus fm is minus 5. Totally you get the minus 15. So here also see the difference is a 5 5 1. Got it, my students? So like that, it is a periodically, it is repeated the signal towards the right side and towards the left side. Okay. So you'll little bit confusion. I will explain this in the whiteboard, my students. In the first case, case 1, if I assume the signal x delta of f is equal to fs into x of f, that is when n is equal to 0, plus sum of n is equal to minus infinite to infinite, when n not equal to 0, this one, fs into x of f minus n into fs. And the original signal does not have any frequency components more than the FM. Okay, let us take this as minus FM and 0 FM. So frequency is in terms of hertz. Okay, this is a function of the sampling frequency fs x of f when n is equal to 0. Okay, this is a fs1. Now the case 1, if I am assuming the case 1, fs is equal to 2f, is equal to 2f. Okay, assume, or let us take let fs is equal to, for understanding purpose only, if I am now taking the value, my dear students, fs is equal to 10 kilohertz. 10 kilohertz means what is the FM now? The fs is equal to 2 into 5 kilohertz. 5 kilohertz means it is band limited. The original signal is band limited to the plus or minus for the 5 kilohertz. FM is a 5 kilohertz, and there is no any frequency components more than the 5. FM is equal to 5 kilohertz. So this value is 5 plus 5, and here the value is minus 5. Okay. Now the signal is repeated when n is equal to 1 and n is equal to 2. When it's 0, the same function is a 0 value, and it is a minus FM. The value is a minus 5 plus FM plus 5. So when in this equation, the x of f minus n into fs, when n is equal to 0, it becomes of x of f1. This is when n is equal to 0. This is x of f. Okay. Now when n is equal to 1, the x of f minus fs. Okay. So here the fs is a 0. Now it is shifted towards the right side with the fs samples. What is the fs here? The 10 kilohertz. So I am taking here this fs as 10 kilohertz. 10. So 0 is shifted here. Let us take the 0 is shifted when n is equal to 1. So what is the next value here? Definitely it is equal to 2FM, means the difference is here the 5, and here also the difference is a 5. fs plus, this value is fs plus fm, this point. And this point is already the plus FM. Now I'm writing that as Fs minus Fm. Both are equal here. What is the Fs now? The 10. 10 plus Fm. What is the Fm? 5 here. Fs is a 10 plus Fm is a 5, totally the 15. Okay, it's a 15. And this point, Fs minus Fm. Fs minus Fm. What is the Fs? 10 minus Fm. Fm is a 5 kilohertz. So 10 minus 5 is a plus 5. Got it, my dear friends? So exactly add the plus Fm only, it is repeated the function. So when n is equal to minus 1, if I am taking the minus 1, x of F plus Fm, not the Fm, plus Fs, means minus of minus. Plus means shifted towards the left side as advanced function. So 0, whatever the function here, the 0 is shifted towards the right side with the Fs samples. Whatever we did in the when n is equal to 1. So what is the function here? The x of F minus Fs. Okay. Now it is Fs minus Fs. Minus Fs means minus 10. Minus 10. So 0 is shifted to minus 10. And this term, what is this term? Minus, already the minus Fm is there. So minus Fs plus Fm. What is a minus Fs? Minus 10. Fm is a 5. So minus 10 plus 5 is a minus 5 only. So you'll get like this. Okay. Right. This is when n is equal to minus 1. The equation is x of F minus Fs, not the minus plus Fs. Okay. You get. And the next one is a minus Fs plus Fm. And this is equal to the minus Fm only. Whatever we got. And next here the term is minus Fs minus Fm. It's a minus Fs plus Fm minus Fs minus Fm. Towards the left side and towards the right side of the minus Fs. What is a minus Fs? Fs is a 10, minus 10. Fm is a 5, minus 5. Totally you'll get the minus 15. Okay. In this way, you can shift towards the right side and the left side when n is equal to 2, n is equal to minus 2, and so on. So it is a periodically, it is a repeated the signal. Periodically, it is repeated the signal. Got it, my dear students? So each point in the spectrum, the sampled version of the spectrum, my dear students, which is not the sampled, it having only the x of F, which is not having any components, any frequency components more than the FM. It's a 0. After the sampling only, we got the samples when n is equal to 1, when n is equal to minus 1, and so on. How we'll get the recover this signal? How we can recover this signal? That is by using the low pass filter. Okay. So up to this, I hope you can understood how we get this spectrum, and it is shifted as 0 plus 5 and plus 10 and the 15. See, every point is a difference of the 5 ohm. The total spectrum is shifted towards the right side, and this total spectrum is 3 points. When 0 is shifted, Fs means the plus Fm is also shifted to the 5 points more than the Fs. And minus Fm is also shifted 5 samples less of the Fs. Means plus 5. And so on. Okay. Like that, we got the spectrum like this. Fs plus Fm and Fs minus Fs minus Fm, and this one is a minus Fs plus Fm, and this one is a plus Fm minus Fm. Okay, 10 minus here. Okay, these are all the functions. The Fs minus Fm and this point is Fs plus Fm, and this point is Fs plus 2Fm, and this one is minus Fs minus Fs plus Fm minus Fs minus Fm, and whenever if you can have this function also minus Fs minus 2Fm and so on. Okay, in total the spectrum is 2 omega and omega. See here, Fs minus Fm plus Fs. See these two functions, if I am taking the Fs minus Fm, and here that is a plus Fs is there, plus Fs. Okay, and here the Fs plus omega and Fs plus Fs minus omega. You can subtract those two functions finally, and you can subtract from the Fs minus Fm. You'll get this get cancel off Fs, and you will get the Fm is nothing but the omega and in this function. And similarly here also Fs plus omega, the higher value to the lower value, you can substitute subtract Fs get cancelled, we'll get the omega. See every spectrum it is in the omega and omega, you get the total in the Fs is equal to 2 omega. Okay, the first one is a band limited signal of x of t, and the B, the spectrum of sampled version of x of t. Sampled version of x of t with the Ts is equal to, 1 by the 2Fm. Okay, W, my dear students, here sampling frequency is equal to 1 by the 2Fm, the Fs is equal to 2Fm. Actually, it is a Ts is nothing but 1 by Fs only. What is a Ts is equal to 1 by S. So Fs is equal to 2Fm. So Ts is equal to 1 by 2 omega means it is Fs is equal to 2Fm. It becomes a periodic in Fs. It's a periodically it is repeated with the samples of Fs, 2Fs, minus 2Fs, and so on. Got it, my dear students? The way we can get the periodic spectrum or the sampled version of the x of t signal. Got it? Thus, we see that the periodic spectrum x of f just touch each other at plus omega, plus 3 omega, plus 5 omega. Touch each other. You see here, there is a omega is there here. And there is a 3 omega. 3 omega means 3 into Fm. 3 into Fm is Fm is a 5. 5 is 3 into 5 is a 15. We got the 15, my dear students, when we consider as a Fs is a 10. And minus 3 omega and so on. So all the points is structured. Thus we can see that the periodic spectrum x of f just touch each other at Fm, and there is a 3Fm plus 5Fm, etc. as shown in the figure. Now let us see whether the sample signal completely represents x of t. This will be true if the samples values x of any ts are specified not only at t is equal to ts, but for all the time, you know, from the equation of 5.19. So this is the equation of the 5.19. X delta of f is equal to fs into x of f plus fs into x of f minus n into fs. Okay, this is the same thing. X delta of f is equal to fs into x of f plus sum of n is equal to minus infinite to infinite when n not equal to 0. Okay, fs into x of f minus n into fs. So we have made two assumptions at the start of this discussion. It is a x of f is equal to 0. For f is greater than or equal to omega, there is no any frequency component greater than the Fm value because it is a band limited to the Fm signal, which is Fs is equal to 2Fm sample rate, 2 omega, my dear students. Here I am saying it is a 2 Fm. Okay, we considered that Fm is equal to omega 1. So the equation 1.10 can be written as Fs into x of f is x delta of f. See, the getting in the left hand side, Fs into x of f is equal to x delta of f minus sum of n is not equal to 0, n is equal to minus infinite. Fs into x of f minus n into fs, and x of f is equal to the Fourier transformation of the signal x of t. The Fourier transformation of the x of t signal is x of f. The 1 by fs into x delta of f minus sum of n is equal to minus not equal to 0 minus infinite. The f of s is get cancelled. X of f minus n into fs, where fs is a 2 fm, where this equation can be expanded. Therefore, we get x of t is equal to x of 0 into sinc function plus or minus plus and another sinc function and plus 2s with the sinc function plus 3ts the sinc function. Okay, sinc function means the graph of the sinc function, it is always goes to 0 value. It is a sampled version, and here this is sinc function at the ts, 2ts, 3ts, 4ts, and minus ts. Sinc function is always showing like this. It goes to 0 and like okay, and the ts, 2ts, 3ts, and so on. Means to recover a reconstruction of the x of t from its samples. This is a sampled version of the signal x of t, and is a reconstruction of the signal x of t from the samples of t is equal to n into ts, where the n is equal to 1, 0, 2, and 3, and so on, or plus or minus. Okay, my dear students. The figure what we see now is it shows a sample version of the signal x delta of t, shows a sinc pulses of varying amplitude located at a sampling instance. The peaks of the sinc pulses repeats the amplitudes of the samples. This signal give the equation of the total function when nx is equal to 0, when n is equal to 1, and n is equal to 2, n is equal to 3, n is equal to 4, and so on. Okay. This signal given this equation can be passed through a low pass reconstruction filter. And remember here, this equation or this signal is passed through a low pass reconstruction filter to get a smooth x of t. Means the original signal is recovered by using the filter is a low pass filter. Okay, my dear students. Here we have assumed that minimum sampling frequency should be equal to the 2 omega. Is Fs is greater than or equal to 2 fm. Minimum frequency is 2 fm. Maximum frequency is the Fs. The sampling frequency is greater than the 2 fm. Minimum frequency should be equal to the 2 fm. That is a twice of maximum sampling frequency. The twice of maximum sampling frequency. Thus, the statement of sampling theorem 2 that proved here that a signal can be completely represented and recovered from its samples. So the statement saying that the signal is band limited to FM hertz and is completely recovered by its samples, so that Fs is greater than or equal to Fm. It is proved here that the signal can be completely represented and recovered. Completely represented and recovered from its samples if the sampling frequency is twice the maximum signal frequency. Fs is greater than the 2 fm. Okay, my dear students. Now in the next class we can see that how we can reconstruct the signal by using the filter of low pass filter for the case of Fs is greater than or equal to Fm. and what is the spectrum will get for the FS is less than the FM, that is aliasing effect. Okay, madam.